Good evening once more. Today, we'll be looking at one of the foundation topics in chemistry. We are still at the foundation level, and this level is very, very crucial if you are going to pass this chemistry exam, because they are the things that is going to help you when you get into the main thing in chemistry. So today we are going to talk about Mole Concept and Stoichiometry. So the importance of these two topics, that's why I said they are the foundation topics in chemistry, because they help us to understand so many things. And when you even go higher, you also see the importance of this thing in medications and every other things you are going to be doing there if you are the ones that if you are going to pursue medicine and medical course. So let's okay, at the end of this class, we expected that everyone who attended this class will understand fully what atomic mass is, what isotopy is, and how mass spectrometry works. Then be able to define more and apply the Avogadro's constant. Then differentiate between differentiate between empirical and molecular formulas. Then apply stoichiometry concepts as molarity, then mole fraction and mass concentration. So without wasting our time, our first topic today is mass is atomic mass. They say that atomic mass is the weighted average mass of an atom based on isotope. Atomic mass is the average mass of an atom. I know that atom is the smallest unit made up an element, smallest indivisible unit of an element. And then this element that has atom, the average weight of this, the weighted average mass of an atom is what we call atomic mass. You can bring it down like when you have a fruit in a basket and you want to find the average weight of the fruit. Maybe the basket has a varieties of fruit in it, and you want to find the average weight of each fruit inside the basket. So that's just like your atomic mass. It helps. It is the weighted average, the average mass of an atom, and is based on isotope. So talking about isotope, you say that every element, as you know, has an atom, and each atom has a mass. The mass of this atom is what we call atomic mass. But now, not all atoms of an element weigh exactly the same. We have an atom in every element, and all this atom has a mass. But not all the atoms of an element weigh exactly the same. Why? I say because of what we called isotopy or isotope. So looking at all we have here, isotope of chlorine. We have chlorine 35 and chlorine 37. So the first one is a lighter chlorine, and the second one is the heavier chlorine. because you normally make use of the first one. In your periodic table, what you're going to see there is the first one. So if you are going to find the average atomic mass of this chlorine, then we are going to use the formula M1 times M2 plus M2 times M1 times A2 plus M2 times A2. We know this M1 and M2 has atomic masses of these two isotopes. Then the A1 and A2 are their respective abundance. So given that the atomic mass of chlorine, the first one is 5, while that of the abundance is 75%, or 0.75 in decimal. Then the chlorine is 37, the atomic mass is 37, and the abundance is 25. Then to find the average atomic mass, so that 35 times 0.75, what you get from it, you add it to 37 times 0.25, and it will give you this 35.5 that you normally see in your periodic table. So the average atomic mass of chlorine has two isotopes. So the abundance of the first isotope, which we call the lighter chlorine, is 75%, and the abundance of the heavier chlorine is 25%. So this gives you 100%, right? When you want to find the average atomic mass of these two elements, then of these two isotopes, then you have to times the atomic mass of the first one with the abundance, and then do the same thing in the second one. And whatever you get, you add them together, and it's going to give you your 5.5, which is the average atomic mass of chlorine. Then, like you said, that not all atoms of an element weigh exactly the same due to isotope. So what is isotope? The isotope are elements with the same atoms. Sorry, they are atoms with the same number of protons but different neutrons. They are atoms that have the same number of protons but different neutrons. So we have so many examples here, like your carbon 14 and carbon 12. You have your hydrogen. You know that of hydrogen, right? Hydrogen has 3 isotopes, and then the first one is your protium, and then your deuterium, and your tritium. Then we have the uranium 235 and uranium 238. Then we also have that of oxygen 16 and oxygen 18. So many other elements. I think phosphorus also has isotopy. So many elements exhibit this phenomenon, that a situation or a phenomenon where atoms has the same number of protons but different neutrons. So this can be used mainly in radiocarbon dating. So when we get to that aspect, we explain how we use this thing more better. Now we'll talk about this mass spectrometry. Mass spectrometry is defined as an analytical technique used to determine the mass and abundance of an atom or molecule by separating their ions based on mass to charge ratio. Now, this mass spectrometry is very, very important in chemistry. So it's very, very important as far as chemistry is concerned. Why? One of the main reasons this mass spectrometry, or the main reason actually, is that this mass spectrometry is related to chemistry and it is very, very important in chemistry, is due to the role it plays in isotopy. So this atomic mass isotope mass spectrometry, they go hand in hand, they work together in the sense that isotopes helps you to understand why every element has the same has atoms, and then each atom has a mass, but not all atoms of an element weigh exactly the same. The phenomenon that explains this is isotope. Now, what is the role of mass spectrometry in relation to isotope? So we can't talk about isotopy without talking about this mass spectrometry, because they help us to understand how isotopy exists, how this thing come about, or how to know that this element is an exhibit this isotope. It is this mass spectrometry that can help us to understand it. So we say that it is a powerful technique or analytical technique that separate atoms or molecules based on their mass to charge ratio. Now, when elements are analyzed using a mass spectrometer, different isotopes of the same element show up as separate peaks, or what we call separate lines. If an element exhibits this isotope, it's going to show different peaks or different lines. You can call it peaks or lines. And then it has first of all shown that okay, the element you are testing for is an isotopic element. It exhibits this isotope. Then the next thing is that it's also helping to understand the number of isotopes these elements have. Helps you to understand you know. Now let's bring it down to our daily activity. Imagine you have a machine. You have a machine, or let's say, okay, mass spectrometer is already a machine. Let's say, imagine you have this mass spectrometer that can weigh atoms. Now, when you put this atom into it, it can turn it into ions, then speed them up. When it speeds them up, you send them through a magnetic field, and then you check how much they bend as they pass through. That's simply how mass spectrometer works, or how this mass spectrometry helps us to detect isotopic elements. So when you put in that atom or that element that has atom, of course, every element has an atom. So when you get an element and you want to check whether this element has exhibit this phenomenon called isotopy, you can put it into a mass spectrometer. When you put it into mass spectrometer, it turns them into ion. It ionize them. When you look at our screen here, it's showing the basic principle that this mass spectrometry follows. The atoms or molecules are ionized to form positively charged ions. Then these ions are accelerated or speed up. You speed them up, and then you send them through a magnetic field. They pass through a magnetic field. Then this magnetic field now deflects ions based on their mass and charge. And a detector records the ion showing mass to charge ratio and relative abundances. When an element let's say an element has a three isotopy, or yes, isotopy, and then you pass it through this mass spectrometer, it ionizes this element, and after ionizing it, you speed them up, and then you send them through a magnetic field. Now, if it exhibits isotopy, is going to deflect based on the number of isotopes it exhibits. If it's true, the lighter one will deflect, and the heavier one will also deflect. The lighter one will bend, the lighter one will bend more, while the heavier one will bend less. So if it does not exhibit isotopy, it will create just a straight line or a straight peak. So let's use this chlorine for example. Let's use chlorine for example. You have chlorine part 5 and we have chlorine part 7. We call the chlorine part 5 the lighter chlorine, and the other one has the heavier chlorine. So when you pass a chlorine element through this mass spectrometer, it helps you to show that this chlorine has more than one exists in more than one form, that it has an isotope, it exhibits this isotopy, and then the lighter one will bend more and the heavier one will bend less. So the main component of a mass spectrometer, the ion source, that convert this sample into atoms or this molecule into ions. This is very important because it cannot exhibit other process without this. When the elements you put there, the atoms need to be converted first before any other thing can take place. Then the next one is the accelerator. This helps to speed up the ions, to increase the speed at which these ions accelerate. Then we talk about the deflector that uses a magnetic field to separate ions based on their mass to charge ratio. Then also we have the detector. This measures the deflected ions and then produce a mass spectrum. Now, I said that there's some applications of this mass spectrum, this spectrometer. It helps to determine isotopic composition of elements. Of course, you said that when you have an element with you and maybe in the lab or as a chemist and you are confused whether this element is bit isotope or not, it will help you to know the one that exhibits such phenomenon or not. Then it also helps us to calculate the relative atomic mass. And then it helps us to identify unknown compounds. Then it is used in forensic science, in drug testing, and space research. To talk about the Mole concept. The Mole is one of the most powerful knowledge of chemistry or knowledge you need to have or understand very well in chemistry. Now, when we want to buy a carton of eggs, or when you bought a carton of eggs, how many egg is inside? That's 12. Now, how am I going to put this? A mole is the amount of substance containing Avogadro's number of particles. Now, how do you come about this mole? So that when you buy a carton of eggs, it contains 12 eggs inside. Now, chemists also count things. They also count different things, and atoms is the major thing that we do count. Now, you remember we said that atoms are indivisible and they are very, very tiny. So we cannot start counting atoms one by one as you can count eggs. We need to find a way or a bigger unit for them that we can we can use to count these atoms. And that's where this one mole comes in. Because a mole contains an Avogadro. A mole contains an Avogadro constant. One mole is equal to 6.022 exponential 23. Now, let's break it down more. one mole of an atom, of an atom weigh, let's say 1 mole of an atom weigh 1 gram, yes. 1 mole of oxygen, for example, weigh 15 grams. Now, if you have to find the 1 mole of water, if you have to find 1 mole of water, that's we're giving you like, I think, how are you going to find this? Suppose you have you are asked to find 1 mole of water. Hydrogen is 2, and then oxygen is 16. So 2 plus 16 is going to give you 18 grams. Importance of mole. Mole helps us to convert atomic scale to real world quantities. So, for example, how many atoms are there in 5 grams of calcium? So, first of all, you have to find the mass of calcium. This is 5 grams given to us here. Then the molar mass of calcium is 40 grams per mole. Then the Avogadro number is 6.022 exponential 23 atoms per mole. Now, the first step you have to do is to, first of all, calculate the moles of calcium. The moles of calcium, a mole of calcium equals to mass divided by molar mass. Your mass is 5 and your molar mass is 40. When you divide it, it's going to give you 0.125 mole. Then the second step is you multiply this mole by Avogadro number. The number of atoms is 0.125 times 6.022 exponential 23. That will be giving you 7.5275 exponential 22 atoms. You can even stop using if you're asked to find a something like we are giving a 36 grams of water, and we are asked to find the number of moles. We are giving 36 grams of water, and we ask how many molecules is inside it. That's very easy. First of all, like you said here, you first of all find the molar mass of water. The molar mass of water should be giving you 18, and then you divide the 18, you divide 36 with 18, and you get 2. Then that 2 times it by Avogadro number, which should be giving us, I think, 1.2 exponential 24 or something like that. So let's talk about the empirical formula and molecular formula. Molecules are represented in various ways.
Hello? Hello?
Can you hear me? Can you guys hear me?
So please, can you have a recap of that mole concept, please? I didn't understand it very well.
Okay. Concerning mole concept, you see that a mole is the amount of substance containing Avogadro number of particles. And I say that Avogadro constant is 6.022 exponential 23 particles or mole or per mole. Now, what I explained there is, I said if you go to the market and then you buy a crate of egg, that crate of egg contains 12 eggs inside. It contains 12 eggs inside. Now, he said that chemists find it difficult to name atoms based on atoms are very tiny and they are very, very large. They are very many and they are very tiny. So we need to find a common way we can name this atom so that it can be easy for us. And then we come up with this thing called mole. So this mole helps us to group these atoms based on this Avogadro constant. That one mole is equal to 6.022 exponential 23. Just as we can see, one crate of egg is equal to 12 eggs. Contains 12 eggs. You can see that one mole contains 6.022 exponential 23 particles per mole. And then we talk about how to use this mole to solve questions. And I said that one mole of atom weigh 1 gram. That if you are asked to find a mole of something like oxygen, you should know that oxygen is a diatomic molecule, so it should be 0.2. It should be written as O2. That means 8 times 2 should be giving us 16 grams. And then there is an example here where we are asked to find how many atoms are there in 5 grams of calcium. So that when we face this kind of problem, first of all, we should find out the mass of calcium, which is giving us here 5 grams. Then the next thing after finding the mass of calcium is to know the molar mass of the element. The molar mass of calcium here is 40 grams per mole. And then we find the Avogadro number, which we know that is 6.022 exponential 23. And then begin our calculation. First of all, let's calculate for the moles of calcium. This is mass over molar mass. That's 5 over 40. 5 divided by 40 will give us 0.125 mole. Then after that, remember we said that 1 mole is equal to 6.022 exponential 23. So to find the number of mole giving us in this to find the number of atoms giving us in this 5 grams of calcium, what you need to do is that mole we get, we times it by Avogadro number to get our final answer. So when we do the calculation, it will give us 7.5 if you approximate it exponential 22 atoms. So we are talking about the empirical formula and the molecular formula. So that molecules are represented, and then these molecules can be represented in 2 ways: the empirical formula and the molecular formula at your level. As you go up more, and when you enter your 004 and 003, you see that you can also represent molecule in structural formula. Either you represent it in empirical formula, molecular formula, or the other one, which is called the structural formula. But the most commonly used one is your empirical formula and your molecular formula. Now, I'm talking about the molecular formula. You see that molecular formula is the simplest ratio of atoms in a compound. The simplest ratio you can get of an atom in a compound. Why the molecular formula is the actual number of atoms in a compound. So let's say that this empirical formula gives us a skeleton of a compound, just like telling us that this compound has a carbon inside, it has a hydrogen inside, it has an oxygen inside. But when we want to know the actual number of atoms, the actual number of chlorine, of carbon, of hydrogen, or oxygen in that compound, we make use of our molecular formula. So let's solve an example here. We are giving them this glucose, you know that for the empirical formula, you should be getting something like CH2O. But to find the molecular formula, the actual number of atoms of carbon, of hydrogen, of oxygen that are present in glucose, we use this molecular formula to get there. So I say that to verify or understand the relationship between empirical formula and molecular formula. So first of all, this empirical formula is the simplest whole number ratio of atoms in a compound. For example, for glucose, you say that the empirical formula is CH2O. Then the molecular formula, which is the actual number of atoms of each element. Let's say when you get a banana, you can say that or maybe when you get a basket of fruits, you can say that okay, there is one bunch of banana here. There is orange in the basket. There is banana. There is carrot inside it. But when you want to find out the actual number of banana inside it, you can say there are 12 bananas, there are 5 oranges, there are 15 purples, and a lot of them. So what I'm trying to make you understand is that empirical formula will just give you the simplest whole number ratio that they can get in that compound. Why, if you want to actually know that, okay, for this compound now, what is the actual number? What is the exact number of the atoms in it? You make use of your molecular formula. So when solving for any calculation, you cannot get your molecular formula without first of all passing through your empirical formula, unless the questioner or the examiner decide to give you your empirical formula beforehand. But if the question comes like that, maybe it comes in form of a percentage, and then you get to solve, and they ask you straight, because sometimes they can ask you straight to give them just the molecular formula. They are also indirectly asking you to give them the empirical formula. So if you're asked to determine the molar mass of this glucose, carbon is 12 grams per mole, then hydrogen is 1 gram per mole, then oxygen is 16 grams per mole. And the molar mass of this is CH2O, that's 12 plus 2 plus 16, be giving us 30 grams per mole. And the molar mass of the glucose, we want to find the molar mass of the glucose, then C6H12O6, 6 times 12, 12 times 1, 6 times 16. That will be giving us 180 grams per mole. So now, if you're asked to find, if the question also asks us to find the ratio between the molecular mass or empirical over empirical mass, or if they flip it and ask us to find the empirical mass ratio over molecular mass ratio, depending on the one they ask you, then you can divide it with the other. If the first one they ask you over the second one, if they ask you to find the ratio of molecular mass over empirical mass, that's what you get in your molecular mass. You divide it and what you get in your empirical mass. So to get this your empirical mass, is add when you are given a compound, if you're actually given a compound and then you're asked to find the empirical mass and the molecular mass, just add the compound, give it to you in your empirical discipline. In your question, as an empirical formula, you add it together, and then the molar mass is what you're going to use as your empirical mass. Then the second and the next one, whatever they give you as your molecular formula, just find the molar mass of that of the atoms of that compound, add them together, and then use it as your molecular mass, and then you can easily find the ratio.
So I'm sorry for taking you aback. This last explanation, I didn't get it well.
Okay. What did you not understand, please?
Where you say if you are asked to find this, you use this and divide this and other ones. I didn't understand it. If
Okay.
you were asked to determine if you are asked to determine the molar mass of glucose, from there down, I didn't get it well.
Okay. So the empirical formula is the simplest whole number ratio of an atom or of atoms in a compound. And then the molecular formula is the actual number of atoms of each element in a molecule. The actual number of atoms of each element in a compound. Sorry, that's a mistake. So we are using glucose as an example here. And then we are trying to solve this, we are trying to understand the relationship between this empirical formula and the molecular formula. And then we say that there are, if you are asked to find the relationship between this empirical formula and the molecular formula, it simply means you are asked to find the ratio between these two things. Sometimes they can ask you to find the ratio between the empirical mass and the molecular mass, or they can simply ask you to find the ratio between the empirical formula and the molecular formula. Or they can even flip it and ask you to find this over the other one. So now, if you are asked to find the ratio between the empirical mass and the molecular mass, you say that whoever that is giving you the question must have given you an empirical formula for the compound he or she wants you to find the empirical mass. And we give you the molecular formula for the compound he or she wants you to find the molecular mass. So the easy thing you need to do is to know the molar mass of each atoms in those to know the molecular mass of all the atoms in that compound, then add them together, and that gives you what you need. Okay, for the empirical formula, for the empirical mass, you say that the empirical formula given us here is for glucose, CH2O. So we need to find the empirical mass of this CH2O, which is simply adding the molar mass of this of the atoms in this compound called glucose. So the carbon has 12 grams. The carbon molar the molar mass of the carbon is 12 grams per mole. That of hydrogen is 1 gram per mole, and that of oxygen is 16 grams per mole. If it is not it is not hydrogen, because hydrogen is 1 times 2. That's 1. 2 times 1. Hydrogen is 1 gram per mole, then oxygen is 16 gram per mole. So if you want to find the empirical mass, looking at the formula they give us here, CH2O, C is only 1, carbon is only 1, so it's 12. Hydrogen is 2 moles here, so 2 times 1 will give us 2. Then oxygen is 16. Then you put 12 plus 2 plus 16, it is going to give us 30 grams per mole. That 30 grams per mole is what we call our empirical mass. You understand now? Is what we call our empirical mass. We keep it aside and then find our molar mass for that compound for glucose. So from here, our molar mass is given as our compound here as molecular formula is given as C6H12O6. That's 6 moles of carbon, 12 moles of hydrogen, 6 moles of oxygen. So to find the molecular mass here, all we need to do is to times the number of moles we have here with the times the number of moles we have here with the mass. So this 6 times 12 plus 12 times 1 plus 6 times 16 is going to give us 180 grams per mole. And then we are asked to find the ratio. Ratio is simply divide this over this. So if you're asked to find the ratio of molecular mass over empirical mass, that is 180 over 30. If you're asked to find the empirical mass over molecular mass, that is 30 divided by 180, that's 1 over 6. So we now understand how we get this empirical mass and how we get this molecular mass. So in conclusion, here what we are trying to point out is that when you are given an empirical formula CH2O, and then you are asked CH2O, and you are asked to find the molecular formula, they're supposed to give you like a kind of a figure. But when you add this CH2, the molar mass of this compound together, you divide it by that figure, and whatever you get, use it to times this thing. Use it to times this the atoms here to get your molecular formula. The molecular formula is the actual number of atoms that are contained, that are inside that compound. Why the simplest atom in that compound is what we call the empirical formula. So if you want to know the exact number of atoms, we can make use of we use what we call the molecular formula. So
Thank you, sir. I understood it very well now.
okay, we move over to quantitative study of reactants and products. So we know that whenever it comes to JUPEB, there's a part of JUPEB that deals with your practical. There's a part that deals with your theory and your objective. So whenever you do theory,
there is a topic you brought out before I ask that question. It's not this one. There is another topic you brought out. You've not thought of that one.
Is it this topic?
I'm just seeing stoichiometry. Not this one.
This is the semester overview. The next slide that we are about to look at.
There's nothing in it. Say next slide.
So, let's talk about the quantitative study of reactants and products. So the quantitative study of reactants and products in a chemical reaction involves using balance equation to calculate the amount, the mass, the mole, or volume of substance used and the amount produced. Now, stoichiometry is a science. Stoichiometry is science of measuring and predicting what happens in chemical reaction. Like something I was saying before, and someone does my attention back. I said that when you are doing JUPEB, some topics you do here, you also practice them. So this stoichiometry is more like a practical aspect of chemistry. But you can also use it to answer theory questions in the aspect of learning how to balance a chemical reaction very well. So let's say something like we are trying to bake a cake here. So we need 2 eggs to bake 1 cup of flour. Now, if I have 6 eggs, how many cup of flour do I need? So that's just what stoichiometry is all about. Trying to balance the reactant and the product. Now, we know what reactant and the product is. Reactant is the substance you use. Remember the difference between a physical reaction, a chemical reaction, and a physical reaction. I've forgotten. I remember that a chemical reaction is that in which new products are formed. So the substance you use to form a totally new substance is what we call the reactant. And this new substance that you form is what we call the product. In which sometimes it can go both sides. The reactant can be a product, the product can also be a reactant. Where and then we call that the system to be in equilibrium, when the reactant can go back like how it is in the formation of ammonia. The reactant can form the product can also form the reactant. So yeah, our main focus is to know how to balance a chemical reaction very well. So now, why this stoichiometry is very, very important is that it helps us to predict how much product will be formed to ensure that no excess waste of reactants happens. Then it is crucial in industry, in the cooking, in the pharmacy. Now it helps us to predict how much product will be formed. From the reactants, you already know that if you have 2 mole of hydrogen here and you have 4 moles of oxygen that are there as your reactants, and then you can predict that it is 2 moles of water that is going to form. So you have something like 1 mole of nitrogen, and you have 3 moles of you have 2 moles of nitrogen, and you have 3 moles of hydrogen. You already know that you're going to have 2 moles of ammonia forming. So this helps us to understand or to predict the number of number of mole or how many products or how much product or even the product that is going to be formed. This stoichiometry helps us to fully understand the products and can even predict them through the reactant side. Or when we have a product that can disassociate from the product down to a reactant, in the sense that we have different types of reaction. We also have what we call this association reaction, in which a product can break down and thereby act as a reactant to form a new product. So this can also help us to know the reactant that helps to form this product. Then it can also ensure that there is no excess waste of reactant. So the main aim here, like I say, is to balance your equation. When you are performing your practical, to know the exact amount that you're going to use so that you do not waste it or that you do not allow excess to go in where they are not supposed to go in. Then it is used in industry, in cooking, it is used in pharmacy. In pharmacy, it's used in medicine and so many areas of life. Now, just as they say, a recipe tells you how much flour or sugar to use. Then a biochemical equation tells you the exact proportions of chemical needed. If we are to form 2 moles of water, we already know that we need 2 moles of hydrogen and already need 2 moles of hydrogen and 1 mole of oxygen. So let's look at some questions. What mass of water is formed from 10 grams of hydrogen? First of all, remember that when you are trying to balance an equation, when you are given two equations, two reactants or three reactants, and you're asked to form a product, that you first of all look at the numbers of these products, look at the number of moles each of the products is, and try to predict what is going to form at the other end. What is going to be the product. And then when you're able to predict what's going to be the product, you look at the number and check whether the number here balance with the number on the other side. If the number here does not balance on the other side, then you try to balance it. If you have two here, two should be also here. If you have 2 moles of nitrogen here, that same thing should be here. So that's what this stoichiometry is trying to help you to understand as a student. Like you said when we started this class, that this is a foundation aspect of chemistry. So as you go into this chemistry meeting so many problems, doing so many practicals, you see that balancing chemical equation is what you are meeting on your everyday activity as a chemist in this chemistry in this chemistry issue, like how you, as you solve chemistry problems, you surely meet this balancing equation of a thing. So you need to understand that for you to have a balanced chemical equation, what is on the left hand side must be the same thing on the right hand side, and vice versa. Then our question here is that what mass of water is formed from 10 grams of hydrogen? So first of all, we balance the equation. You have 2 moles of hydrogen, you have 1 mole of oxygen, and that gives us 2 moles of water. Then after balancing our equation, next thing we need to do is we need to find the molar mass. So the molar mass of hydrogen is 2 grams per mole. The molar mass of water is 18 grams per mole. Then you convert the grams of hydrogen to moles. So moles of hydrogen is, remember what they say, what mass of water is formed from 10 grams of hydrogen. So the mass of hydrogen given to us here is 10 grams. And they are now asking us what mass of water formed from this 10 grams of hydrogen. So to convert this mass to mole, that's the gram of hydrogen to mole. You do moles of hydrogen equals to 10 divided by 2, which gives us 5 moles. Then step 3 is that you use the mole ratio. From the equation, remember your equation that you balanced 2 moles, 1 mole, 2 moles. Then from your equation, 2 moles of hydrogen gives us 2 moles of water. So 5 moles of hydrogen will give us 5 moles of water. So step 4 is to convert moles of water to gram. Remember our question didn't stop. If our question stopped at how many moles of water is going to be formed, then at step 3, that's where we are going to end our calculation. And tell them that since 2 moles here form 2 moles of water, 5 moles of hydrogen, we also form 5 moles of water. But we are asked to find the mass, which is the gram. So we need to convert the moles back to gram. Remember here we converted the hydrogen from mass to mole. And after finding our mole, we need to convert this mole back to mass. Remember that whenever you are doing your calculation, it must end with what they ask you to find. If they ask you to find something in centimeter, it should end there. If they ask you to find it in dm cube, it should be there. If they ask you to find it here in moles, in any unit they ask you to find. So even if you do your conversion to solve it, at the end, you convert it back and make sure that it is in that same unit they ask you to submit. So The step 4 is to convert these moles of water back to gram, to convert the mole back to mass. So the mass of water is 5 moles of water we got from step 3 times this 18, which is the molar mass of water, will give us 90 grams of water. So 90 grams of water is what we produce. So from this question now, you can easily say that 10 grams of hydrogen will give us 90 grams of water. I don't know if anybody is confused. Do you have
Hello, sir. Please repeat that the last step, step 4.
Therefore, I'm talking about the conversion of moles of water back to gram. And I say that in chemistry, whenever you are given a question and you are asked to submit your answer in so unit, in a particular unit. So whatever you did, after solving your calculation, you must bring it back to that unit, even if you converted before, so you can solve your calculation. Let's say they asked you, they gave you a temperature in centigrade, and then they ask you that the final question, the final answer should be in centigrade, and then you have to convert it to Kelvin so that you can solve what you want to solve. If you convert it, after solving it, you need to convert it back to centigrade. So that's actually what step 4 is all about. Step 4 here from our question, we are not asked to leave our answer in moles. We know that 2 moles of hydrogen gives us 2 moles of water. 5 moles of hydrogen will give us 5 moles of water. But we are asked mass of water. We are asked to leave our answer in gram. So we need to find the mass of water. I know that mass is measured in gram. So we need to find the mass of water. Mass of water mass of water is 5, which is your mole times your molar mass. That's a mole times molar mass. Moles of water times molar mass of water, which is 5 times 18, to give us 90 grams of water. So it takes 90 grams of water to be produced from 10 grams of hydrogen, or it takes 10 grams of hydrogen to produce 90 grams of water. So that's all we're trying to say from that angle, or from that answer. Then molarity. Now, when I'm going through the prep past question, this normally comes, even during my own exam, they always ask this question, the difference between molality and molarity. So the molarity here, moles of solute per liter of solution. Molarity is the number of moles of solute dissolved in 1 liter of solution. So the formula for solving this molarity is moles of solute. From your definition, you can easily depict the formula, or if you know the formula, you can flow from the formula to find the definition. Moles of solute all over volume of solution, and volume is measured in liter, or you can say volume of solution in liter. So, for example, if you have to find the molality of 5 grams of sodium chloride in 250 milliliter of solution. Now, first step is to know the molar mass of the compound given to you, which is sodium chloride. Molar mass of sodium is 23. That of chlorine is at 5.5. That will be giving us 58.5 grams per mole. You know that. You know how we find this molar mass of sodium chloride. We know the molar mass of sodium, and also we know the molar mass of calcium. We add them together, and then we get this. Then the next step is to know the moles of this sodium chloride. We have discovered the molar mass. The next thing you want to discover is the moles. How do you find the moles? Moles are equals to, go back to our question. Our question says, what is the molarity of 5 grams? That is, the mass of sodium chloride given to us here is 5. The formula for finding moles is mass over molar mass. Your mass divided by your molar mass. So the mass given to us here is 5 grams. And then your molar mass is 58.5 grams per mole. Now, why is our unit in mole? Our unit, which is 0.0855 mole, is the reason why it's a mole is the first this thing there, which is our mass, is in gram, 5 grams. Then our molar mass, which is 8.5, is in gram per mole. The gram there has already cancelled the gram under, leaving us with just mole. That's why our answer is in 0.0855 moles. Then the step 3 is to convert this mole now into liter. Remember what I said, that whenever you are solving your question and you are nearing your final answer, or you want to submit your final answer, make sure you put it back to the unit they ask you to submit it with. Now, from the question, they ask us that it should be in liter of solution. So volume of solution is in liter. To convert volume to liter, 250 milliliter equals to 0.2250 liter. Then you calculate the molarity. Molarity equals to 0.0855 all over 0.250. That's your moles, the moles of the salt given to you all over the liter, the volume you converted to liter. Sorry, the volume you converted to liter. Then when you divide this thing, it will be giving you 0.342 mole per liter. I don't know if anyone is confused at the calculation. Is there anything you did not understand?
Right on, sir.
Now the brother to molarity is molality. Now, molality is mode of solute per kg of solvent, moles of solute per kilogram of solvent. This is the number of moles of solute dissolved in 1 kilogram of solvent. Now, what is the simple difference between this molarity and molality? Now, molarity is number of moles of solute dissolved in solution. Solution should be in 1 liter. We are talking about 1 liter. Number of moles of solute dissolved in 1 liter of solution. But for molality, this is number of moles of solute dissolved in 1 kilogram of solvent. So now the difference between both of them is that this number of this mole of solute is dissolved in solution. In molality, while this one it is dissolved in solvent. Now remember I was talking about one. So for solution, it is for solution it is in volume. Sorry, for solution it is in liter. So 1 liter of solution. Then for solvent, as 1 kilogram of solvent, not solution. Your molality is the one that has something to do with solution. While your molality here is the one that has something to do with solvent. So the solvent and the solution is the only difference between two of them. Now the formula for this is mole of solute divided by a kilogram of solvent. Now, if I ask to calculate If you're asked to calculate the molarity when 10 grams of solute is dissolved in 500 grams of water, assume solute sodium chloride molar mass is 8.5 grams per mole. Now, this is our question. We are asked to calculate the molarity when they dissolve 10 grams of solute, and then they ask us to assume that the solute they dissolve is sodium chloride in 500 grams of water. Now, first step is to find the mass of solute. To find the mass of solute, the mass given us here is 10 grams of solute divided by, to find the moles of solute. To find the moles of solute, remember what we normally do, the mass divided by the molar mass. So the salt we are working on, we should assume it is sodium chloride, and they gave us 68.8 as the molar mass. And then they gave us 10 grams as each mass. So the 10 grams should be divided by the molar mass, which is 68.5, giving us approximately 0.171 mole. Of course, remember that the gram, cancel the gram under, giving us with the mole. And of course, remember that anything moles or solute, the unit is in mole. Then step 2 is to convert the solvent mass to kg. 500 grams. Remember your definition. Your definition said 1 kilogram of solvent. So you need to convert this solvent mass to kilogram. 500 grams of mass is equal to 0.5 kg of that mass. Now you calculate your molarity. Your molarity is from what you get in step 1, bring it down 0.171 mole, which is your mole, divided by 0.5 kilogram of the mass. Kilogram of mass given mass of the salt given to you. Sorry. So when you divide, you get 0.342 mole per kilogram. Now your molarity is 0.342 mole per kilogram. Now your first distance 0.171 mole. Then the second one is 0.5 kilogram. That's why your unit is a mole per kilogram. Please, when you do your solving, and then you know that this thing, the figure that you put together has a unit, you can easily generate your final unit from both of them, from the numerator and the denominator, the attached unit there. You can just do your normal distance. If there's anyone that have appeared on top and also appear on the bottom, you do it out. Then the one that did not appear, you can write them starting from the unit in the numerator and end with the unit in the denominator. So from this thing is 0.342 mole per kilogram. Then your mole fraction is the ratio of mole of one component to total moles. The formula is mole A divided by mole A plus mole B. This is just like when you are giving two compound. When you are giving 2 compound, or you are giving 4 compound or 5 compound, you add them together. Then you pick the first compound, divide it by the total number of addition of all those compounds together. Let's say you are giving something different figures that are 5 in number or 2 in number. When you add them together, and the first number divided by the total number gotten from addition of all the numbers together. That's your mole fraction. So if you are asked to find mole fraction of ethanol in a mixture, find the mole fraction of ethanol in a mixture. Then if you are giving ethanol, which is C2H5OH with 46 grams, then you are giving water with 46 grams as its mass, sorry. Then we are giving water, which is H2O, with 54 gram has each mass. And then you say that the molar masses of ethanol, the molar mass of ethanol is 46 gram per mole, and that of water is 18 gram per mole. Now, first step we need to do is to convert masses to moles. The mass is given to us here. We need to convert it to moles. Then, starting from the ethanol, convert ethanol to mole. Remember that they say that remember what they gave us here? They gave us a mass and also gave us the molar mass. The molar mass of ethanol and the mass is the same thing. So 46 divided by 40 will give us 1 mole. And then that of water, 54 divided by 18 will give us 3 moles. Then you calculate the total moles in the mixture. Remember what I said about calculating this thing. So total moles will now be what you get in the first one or the second one. If they are fixed, what you get from the first one, second one, third one, and so forth. So after calculating it, then you find the mole fraction of ethanol, or if you have to find the mole fraction of water, you find the mole fraction of water, which is 3/4, or mole fraction of ethanol, which is 1/4, 0.25. So the mole fraction of ethanol is 0.25. Now let's talk about the mass concentration before we round up. The mass concentration is the mass of solute per volume of solution. Mass conc is given by mass of solute all over volume. That's mass divided by volume. So when we are giving a problem like this, calculate mass conc of 20 gram sugar in 200 milliliter solution. So you're asked to calculate the mass conc of 20 gram sugar in 200 milliliter solution, giving the following details. Mass of sugar, 20 gram. Volume of solution, 200 milliliter. When we change it to a liter, it's going to give us 0.2 liter. And the first step is to know the formula for the mass conc. The formula for the mass conc, remember from our definition, is mass of solute, that is divided by volume of solution. So mass of solute divided by volume of solution in liter. So whatever they gave us or whatever they're going to give to you, you divide it, you change it to liter. If it's not in liter, it must be in liter before you do your calculation. Your mass is 20 gram, and then your liter, after you must have converted it from milliliter, will be 0.2 liter. And then when you do your calculation, it will give you 100 grams per liter. That's your final answer. So from our calculation, from everything we did today, I think from your moles, your stoichiometry, and your atomic mass, your isotopes, your mass spectrometry, you move ahead to mole definition, and how mole and Avogadro constant works in hand, or how mole is Avogadro's constant. They talk about how molecules are represented, the empirical formula, the molecular formula. Then also talk about your stoichiometry, the molarity, the mole fraction, the mass conc, and the usefulness of this stoichiometry. So is there any question from all these things? Is there anything that you did not understand, or that is confusing that you still need me to explain?